Hello, everyone. Good morning. Are you listening to me?
Hi, Raquel. Yes, we
Yes.
can listen
Okay,
well.
thank you. Great. So we are just starting, and we have to be very quiet, but very careful about the time. So thanks for joining the fourth annual conference. Thanks for joining in particular this session on statistics and data science in Portugal, driving across generations. And it is a session organized by the Portuguese Statistical Society. And our first speaker is Carolina Marques from the Faculty of Science in the University of Lisbon. And she's going to talk to us about her, or part of her PhD project. Thank you, Carolina. So go ahead, please.
So yes, since we have very few time to present, I'll just start sharing the screen. Can you all see the screen and hear me well? Yes, okay. I'll just put this on full screen mode here. So I'm going to talk to you about my PhD and what I've been doing in my PhD. So it's about statistical and machine learning tools to improve dinosaur classification problems.
Carolina, sorry
Yes.
to interrupt. Try again to share your slides.
Again? Okay.
Yes.
1 second.
It's visible now, Raquel. Carolina,
yes, perfect.
It's visible.
Thank you. Thank you.
It's visible now?
Yes, it's okay, Carolina. You can go
It
ahead.
is?
Yeah.
Then I'll move on. So the first step was to try to understand what was happening in this area of application in paleontology in dinosaurs. So what we did was to evaluate more than 1,000 studies to understand what was happening in terms of methodological steps done for the study of dinosaurs and other paleontological data sets. So what we saw was that there was a huge problem with, for example, codes and data sharing, which actually improved to be quite difficult because one of the main problems in paleontology is that you have very few data sets and very few examples, and it's a finite element. So one of the things that we focused was on that, on trying to develop a very easily approachable code and openly access data sets. And another thing that we saw was that only from the 2020, we saw an increase in the studies that were using statistical and machine learning methodologies, like more robust methodologies. And the main methodologies used were like random forests, neural networks, discriminant analysis, and then there were a lot of problems related to the data. For example, there were data scarcity, bias in the classifications, and bias in the analysis. It was very time consuming to do the classifications, and data imbalance was actually very, very usually mentioned in the studies. And there was a bias on the studied specimens. For example, very few studies actually studied dinosaurs. They studied, for example, pollens and foraminifera, and not like big macroscopic data. So we focused on 3 data sets, 3 case studies. The first one was on isolated theropod teeth, and it was based on different morphometric data, which were different measurements taken by the researchers from the isolated theropod teeth. And what we did was to actually use different methods like random forest, gradient boosting, neural networks, and support vector machines, and try out different, for example, oversampling techniques to avoid, for example, in some cases you had genus with more than 1,000 observations, and then you had like others with like 20 observations. So it was very hard to actually reach to stable results for the different genus evaluated. And then we also evaluated different standardization methods because many people actually did not use or approach standardization before the use of the models, the classification models. For example, for discriminant analysis, it's very important that we do this. And then when we saw the results, we saw that the models actually predicted very well. and that the confusions between the different genus were actually confusions between more similar data, like with similar teeth, like similar measurements done. Then the next study, the next case study, was actually on vertebrate footprints, which included also dinosaur footprints. And what we did was to simulate data because we had very, very few data. So we had to create an application using Unity to simulate data. And in case you are interested, A, C, E, and G are actually simulated footprints, photographs. So what we did was to evaluate how would the model behave when including the simulated data. And what we saw was that if we only use real data and simulated data on the model, on the convolutional neural networks, we had worse results. But as we increased the quantity of the simulated data along with the real data sets, we had actually very good results, especially while using transfer learning from the trained data using the simulated data to the real data. And then when we look at the results, okay, these are some examples of real footprints. Here are like sauropod footprints and theropod footprints, which are dinosaur footprints. And then what we saw was that the confusions in the model were actually focused on, again, similar footprints, because, for example, foxes and coyotes actually have similar footprints. And for example, sauropod and theropods, since we had very few data, what happened was like he understood that, okay, these two are from like rock sediments, so he would confund both of them due to the similarity in the backgrounds. Then we passed to the spatial modeling, because one of the things that paleontologists need to do is find out where can they find new data, new fossils. And to do that, they usually use just their knowledge and some lucky guesses, okay? So what we found out was that it was useful to create actually a probability map, a distribution probability map, to actually find the most probable places where you could find fossils, having into account different information on the soils, on the environment, and, well, the locations that you actually have already from the fossils already encountered. But one problem here, again, is the data, because the data, in some cases, it's publicly available in, for example, paleobiology database, okay? But these databases actually have a lot of errors. So one of the problems is to find actually reliable data sets, because, well, we have the models with this database, having into account this database, but again, we can't be sure this is actually correct. So one of the problems and one of the things that we are doing right now is talking with the government for us to give us data and more reliable data. So what we did was to try to find, like using, for example, different data from the fossil records, like footprints, bones, and eggs, because they are found in different places, especially footprints and bones. Where you find footprints, you don't have bones. So these are the results from a random forest model. We compare different models, and again, random forest actually had the best results. And what we saw was that, for example, the bones are much more common and can be found all around the places in Peninsula Iberica. This area is the Mesozoic era, which is the era where the dinosaurs lived. And in the footprints, for example, you have a very good cluster here. Sorry, a very good cluster here, because footprints actually are found in more clustered areas. And then the eggs are much scarcer because there are very few information on eggs, especially related to the dinosaurs. And we also used an inland model that actually gave us an idea about the intensity of the process of the points that we saw. You have here the different points, the different locations. And then again, you have the high intensity places where you can find fossil records. And you can see pretty well that the model actually behaves very well. So basically, the idea of this presentation was just to present you the challenges and the possibilities that you have while working with data applied to paleontology. Because in this case, paleontologists actually are very hard to, they are not very happy with statistical and machine learning techniques because they think that these techniques are going to like remove some of their works, like replace some of their works. So they are not very happy with these methodologies, but once they learn that they are capable of doing things and to help them like improve their works, they actually are very happy to learn these tools. But again, you have a lot of problems related to the data because you have data scarcity, data imbalance, even the classifications themselves are very, well, let's say it's not, sometimes it's biased because each scientist, each paleontologist has a different methodology to classification. So it's a science that needs a lot of work in terms of methodological applications, and there's a lot of things to be done. And we are just presenting, I'm here just presenting 3 case studies, but there are a lot of case studies that are important. And we mainly focused on different imagery models and different classification models in terms of, for example, using the different measurements taken by the researchers. And we also focused on like giving researchers like paleontologists a full understanding of the importance of statistics and machine learning in their studies, because it's important that they have reproducible pipelines, open practices, and focus on like correct preprocessing and correct modeling. Otherwise, their results won't be as reliable as they could be. And of course, this work wouldn't be possible without the collaboration with many researchers, including from Portugal, which are my supervisors, and a lot of great people, and also people from different locations like United States, Switzerland, Spain. Well, it's a work group, basically. And I would like to thank the opportunity to present my work here and thank Professor Raquel Nis for the opportunity and for organizing this session. And yes, so thank you. I don't know if I have time, but I try to speed up.
Thank you, Carolina. Thanks so much for your stimulating talk. Very nice talk. Thank you. So please, if you have some questions, please you should post those, or comments. You should post those on the Q&A chat. Okay, so you have the opportunity of doing so through the chat. Let's wait. I think we can, yeah, not that much. Well, anyway, this is being recorded, so I think you'll have also the opportunity of seeing this afterwards and to email Carolina if something should be shared with her. Thank you again, Carolina. So our next speaker is Professor Regina Bispo from the Center for Research into Ecological and Environmental Modeling from the University of St. Andrews, UK. And her talk will focus on the environmental issues. So if you don't mind, Regina.
Thank you, Raquel. I'll try to share my screen with you. Let's see. Can you see it? Yes?
At the moment, yes. So it's perfect, yes.
Okay. Can I start then? Yes? Okay. Okay, so first of all, thank you so much for having me here. In particular, Raquel, thank you for the very nice invitation. So it's a pleasure to be here with you, sharing this special day with so many women around the world. So this is really a pleasure for me. So today I'm going to give a talk about flexible modeling of carcass density gradients around turbines. So a quick overview of my talk. So first, of course, I will briefly introduce the topic. Then I'm kind of going to summarize some of the current methods that are used, show you my new method, the method I'm proposing, and also show you some results from a simulation study. So I think we all can agree that wind farms are actually a good source of renewable energy, but of course this type of structures they are always raising concerns because they have many effects on the environment, and in this particular case on flying vertebrates, so birds and bats. And so there are four main areas of concern. So that includes direct mortality caused by collision, and also the displacement of wildlife, some effects on the migration flyways and fly paths, and also direct habitat loss and habitat changes. And today I'm going to focus only on the mortality caused by direct collision. And so every time a wind farm is constructed, so we need to monitor the fatalities driven by collision. That means that we need to come up with a method to estimate the mortality. And we all know that if we go to the wind farms and count how many carcasses do we find, we actually will find some observed number of dead animals that is obviously distinct. So it's different from the true number, the true mortality. And there are a couple of reasons that can justify this difference. So one of those reasons is the carcass removal. So carcasses are removed by predators, by scavengers. So they are not available to be counted anymore. The second reason is that we are imperfect detectors. So we can never detect 100% of the carcass that are in the floor underneath the turbines. And the third reason, it's because we always have a partial coverage in space. So that means that we don't sample all the turbines, we just sample some of them. And then based on that, we must account for the unsearched area. So I'm going to try to answer this question today, which is how can I estimate then the probability of carcass lying in the covered region? So there are several current methods that are used. A first group of methods that are used today. So there are methods that assume that the carcass density is independent from the distance that we are from the turbine. And actually, we know that that is not true. So if we assume that the carcass density is independent from the distance, then we are assuming that there's a uniform distribution around the turbine. And to correct that, to correct the mortality estimations for that, under that assumption would be really easy, because we just have to divide the number of observed carcasses by the fraction of the area that is sampled. But we know that just making a very simple exercise that really tends to either overestimate or underestimate the true mortality, depending on the density of the sampled area. So on this side, on the left side, you see that you are sampling a more high density area. So you get a very high overestimate. And then on this right side, it's the opposite. So you have low density. So then you get to underestimate, even though the size of your sample, it's exactly the same. More recently, what happens is that people realize that, in fact, the density depends on the distance from the turbine, and so they adapt the methods. And there's a couple of methods and models that have been used. And more recently, what the researchers do, they basically use parametric density estimation. And these authors recently just used GLM framework to generalize the density estimation. So basically what they do, they have a certain observed distribution and they try a bunch of different parametrical distributions and to see which one is the best, that fits the best. So, but if we kind of define the observed patterns, so the observed distribution around the turbines, you get to see this type of densities. So on the left side, you have 8 observed, so empirical densities for birds, and on the right side, you have the empirical densities for bats. And you can see that some of these densities are well behaved in the sense that they are just they have just one mode, but some of them really show us more than one mode and can really be quite wiggly. So what happens if I assume that I'm going to use a parametric model to model something that it's not unimodal? So what happens is that kind of what you see here, the parametric model, which is the red curve, it will not be able to capture the second mode. So because of this, we decided to propose a new method. And this new method, it's just a mixture method between model or estimator between a non-parametric bulk model, which describes the density over the observed domain. That means until the truncation distance. And then we assume a parametric model for describing the behavior at the tail. So in this estimator, if you look at the numerator, what you have basically, so you have here an indicator variable that assumes the value 1 and 0 depending on if you are on the bulk density. So that's 1, for the tail it's 0. And so we are modeling this, the left side of our distribution using the B-spline basis functions to allow for some flexibility. And then on the right side, you just use some simple parametric model. We are going to use the exponentially, but actually you can use whatever you prefer. And this, so basically to use this estimator, it's just about to estimate how these betas coefficients. So to estimate these coefficients, we use the penalized loss function. That means that we introduce the penalized version of B-splines because we want it to be flexible, but we don't want it to wiggle that much, okay? And that was done under 3 constraints. So the constraints of continuity, unity, and non-negativity, in such a way that we are sure that our estimate is the true density. So basically, this is a plot showing comparing the two approaches. On the black line, it's a simulated true density. And the red one, it's a parametric model trying to estimate that density. And in blue, it's our proposed method. So a semi-parametric model. And you can see that it's able to capture actually the second mode much better than the first approach. So going quickly over the simulation process or study. So first we had to define the distribution of the radial distance given detection. So this is basically a product between two functions. One in blue, this is defining our spatial distribution before detection. So this is what we call the state model. And this is basically governed by the carcass fall. And then we have, on the top of this, we have the monitoring process. So we have the observation model. And that is basically represented by a detection function. So if we do the product between, to define this distribution of the radial distances, we defined 3 different scenarios. So one with just one mode. And then the second one, plateau-shaped mixture density. And the third one, bimodal mixture density. And then to simulate the detection, we use this half-normal detection function, and we vary the parameter that defines the detection rate decay. And so if you just do the product between these two distributions, you get these 9 scenarios. And you can see that these 9 scenarios, they are quite close to the observed patterns that we have seen before. So we were actually able to simulate some scenarios that really replicate well the observed patterns. So the second step, once we have defined this function, we have to draw samples from this density. So you use for that the acceptance rejection method, and we establish that as a truncation distance, the 20, 40, and 80 meters. Then after doing that, we had to estimate the density, and we did that using just parametric methods, and also our new proposed method, so the semi-parametric approach. And then we evaluated the model's fit by comparing the estimates to the true density using the mean, absolute error, and also the coefficient between the estimated and the true distribution at the truncation distance. So here you have a figure that allows you to kind of see graphically the simulation study. So first we have our true distribution, then we select a sample from it, which is a truncated sample, and then we try to estimate the true distribution parametrically and using the new method, and then we are going to compare these two estimates with the true one. So some results from this comparison. So first of all, for the unimodal distributions, so what we can see here, it's actually that the difference between the two approaches is not that clear as we expected, in fact, because this is a very well-behaved one modal distribution. So we are not expecting for our flexibility to kind of improve estimates here. But so you can see that the distribution of the error and the ratio between these two values of the distribution function, it's quite similar between the two approaches. But one thing that I would like to underline is that you can see that for the parametric approach, you have a much bigger uncertainty. So the variance, it's much bigger for this parametric approach. So for the second scenario, which is the plateau-shaped distributions, we start to see some advantage of our proposed method. So you can see here, in some cases, that we are starting to lower down the errors compared to the parametric approach. And again, we can see that this blue box plots, they always represent a bigger uncertainty, which is related to the parametric method. And finally, for the third scenario, this is actually the one that we can see really that our method improves estimation. So in the sense that we can really decrease the error, the absolute error, the mean absolute error, especially if you have very low visibility conditions and for very severe truncation distances. And again, it's much more precise, all the estimates that we can get compared to the parametric ones. And in this case, just to show you also that, to underline that, in this case, we are most of the time we are underestimating the value. And here we tend to, on the other scenarios, we tend to overestimate it. So some final conclusions. So both this approaches, both semi-parametric and parametric estimators, they really show very similar performance on the two first scenarios. That means that we have basically one mode. So for that type of scenarios, doesn't really represent a huge advantage to use splines, but in general, our method shows it's much more precise, so it shows very lower variance. So the semi-parametric estimator that we are proposing clearly perform much better when we have more than one mode. So if we have bimodal distributions, and especially if you have the limited detectability, and that means that our method really helps improving the density estimation. So overall, this method is able to deal with any kind of distribution, actually, but it's especially important if we have complex carcass density gradients. So these are some references. And that's it. Thank you so much for having me.
Thank you. Thank you for sharing the interesting work. And we need to move to the third speaker, who is Adelaide Freitas. She's a researcher from the Center for Research and Development in Mathematics and Applications, and she's a lecturer in the Department of Mathematics in University of Aveiro in Portugal. Adelaide, you are sharing your slides. You can start whenever you want, or as soon as you can. Thank you.
Thank you. I hope I think that I share my slide. Okay. So good afternoon, good morning here in Portugal. My presentation will be, I will speak about a singular spectral analysis based procedure that we consider or we propose for explore structural change in time series. It is a joint work with Albert Silva. Okay, the outline of my presentation. First, I will briefly introduce the singular spectral analysis, the steps that we use for this technique that we consider, the algorithm that we propose for detecting change in the time series. In that method, we consider a metric for the compare in order to detect the change. Here we speak about it, and then we give an example with real data when we show the distance that we consider to assessment the structure change in the time series. So let's start with speak about the singular spectral analysis. Here we have so at the beginning a univariate time series with length equal to n. Then we transform this time series in a trajectory matrix. This trajectory matrix is a Henkel matrix. It means that in the anti-diagonal we have the same observation. And if we consider the first column and the last row of this trajectory matrix, we have the time series, the complete time series. So, sorry. So in the singular spectral analysis, we start by decomposing this trajectory matrix in D. So if the D is the rank of the trajectory matrix, we compose this trajectory matrix by the sum of D one rank matrix, and this is what we use in our method. Sorry, I need to take another way to do it. Okay, so so we have our trajectory matrix decomposed in matrix with one rank. Then we apply the Nepal's algorithm to make the decomposition of H matrix with the rank equal to 1. We use the Nepal's algorithm. Why? Because it is handled with the missing values, so it is why we use this, and we obtain the composition of H principal component iteratively. So it's not so consuming time as the singular spectral analysis is singular valued composition, but we get all the eigenvectors, so all the decomposition. So we apply Nepal's algorithm in order to get the composition of H one rank matrix. The decomposition is given by the product of two column vector times row vectors. The first, the T, is the vector given by the score elements that we obtain in the composition, and the other is the loading that's corresponding to the correlation between the components and the axis and the corresponding axis values axis. So in the decomposition of H1 rank matrix, what we want is to get this the score vectors with norm equal to 1. So we multiply and divide by the norm in order to obtain this vector, the t, that the t star that is with norm equal to 1. So the composition of our trajectory matrix is given by this. When the matrix T contain the orthogonal score vectors, the matrix P contain in the columns the orthogonal loading vectors, and the matrix sigma contain the singlet value that corresponding to the norm. Okay, what is the basic idea of our method? Is the decomposition of the same trajectory matrix, but by two different ways. One of the way is using a robust method, and the other is not robust. This is in order to, in the robust, it is not sensitive to the outliers, and the other is sensitive. So when we get some change in our time series, so in the trajectory matrix, the robust not detect and the other detect, and the difference between two of them that give when we have some change in our time series. So the procedure is given by iteration, step by step, how I said in a previous next slides. So the idea of our method is to take all our time series and split it in the sub-series with length equal to m, and for each sub-series to apply the singular spectral analysis. So it means that for each sub-series, we transform it in the trajectory matrix, then we get the decomposition, and we get the composition in two ways, one ordinal and one robust. And we do it sub-series by sub-series, so we shift it one time point at each time. So we have several iterations. This is the first iteration, and so on at the last sub-series of to obtain our our complete time series. So what we do in each iteration, in each sub-series, we consider the trajectory matrix. Then we get the composition in two ways, one robust and the other is not robust. The robust, the difference between them is in the algorithm Nepal, we use in the robust the L1 norm, and the other we use the L2 norms. So we get the composition of our trajectory matrix in two different ways, and we get this part, the score normalized, and when we get with the robust and when we get with not robust procedure. And then we compare two of them, column by column. And so in the first part, we consider the first column of that difference matrix, in the second with the column matrix, and so on. And then we calculate the Frobenius norm for this column, from these two columns, and so on. And this Frobenius norm of each of these sub-matrix is given our matrix. And if we get the last one, we get all the information about the first principal component, the second, and so on. So the direction that gives the higher variability explained variance, the second explained variance, and so on. So we get our metrics, and this is the metric that we use to make the comparison. Give here an example. So suppose that here we have our time series. Here we know that there are a change in the structure of time series. When we get the some subset, some sub-series, in this part we don't any change difference between the ordinal and the robust. But when we get the first point here, when the trajectory metric gets this point, it is an outlier compared with the others. So in the robust method, it's not care. It don't care about it, but the ordinal take in count this. And when it's happened in the trajectory matrix, when we calculate our metrics, we see that the value increase when in times that we consider more subseries that contain more elements of this part. It means that the value of these metrics will be increase. At the end, we get the series that have some parts of this part and the other parts. So it is a balance. So this is why the metric will be established and then down. So it means that in this point, we have the introduction of a value that we have the change point. So the idea is to observe this series with the metrics and to see when we have increased value. In order to apply this, one important step is to determine the number of the length of our series. We propose to do it, consider the maximum of the M, so apply several times for different value of M and to take the value M that maximizes that difference. This is another example. We apply also the same with some series, our method, and we obtain that here at the beginning, we get an increase of the value of the matrix M. It means that in this point, the iteration obtained in the trajectory matrix, the first observation that it's different from the others, and it is mean that here we introduce this point M plus the length of the subseries, and we get what is the time point that we get junction point.
So we have one minute more. Okay, you are finishing.
Okay, thank you. And thank you for listening, and I hope to give the basic idea of our method. Thank you.
Well, I thank the three speakers for accepting the challenging of speaking so complex works and tasks and in so short time. Thank you. Thank you to all and the participants for being here.
Thank you.
Thank you.
See you.
Bye. See you.
See you. I hope in a short time. Bye.
Bye.